Monday, we're going to get a test, as we always do. It'll be our last test, test 5, and it will be on these 5 sections. And there will be 10 questions, 2 from each section. So you kind of know what your test is going to look like. And pretty much that's it, because straight after that, it's finals. So you don't have any extension time because the finals will be upon us, and that's just the way it is. So oops, there's one of my dogs just woke up. Hey, shush, go in, mommy, go on, go in, mommy. First time she ever listened to me, that dog. Must have been the way I said it. Well, where was I? Yeah. So when I first started teaching, one of the good pieces of advice I was given is that if you want students to remember something, you have to tell them 3 times. So here goes. Don't wait until Sunday to do all the homework. You will have a really bad day. Okay. Don't do the homework. Don't leave the homework to Sunday the 6th, or you'll have a really bad day. 3rd time, and here goes. Don't wait until the 6th to do your homework. You'll have a really bad day. Right? We all got that. So I'm not going to settle for, oh, I didn't know. It's your fault. Well, got that bit out of the way. Let's get started with the fun stuff. Applications. For some of you, this is the part of math where you actually say, hey, at least now I know how I can use this stuff. And this is what we're going to be doing under applications. 4 main topics. We're going to find what's called the center of mass, and we're going to do that for a 1-dimensional situation. Then we're going to find the center of mass for a 2-dimensional situation. Neither of these 2 use calculus. Then we're going to do number 3, which we'll get started today. And it's going to be the area, how you find the center of mass from the area of a function under a curve. And then after that, won't happen today, but we'll do hydrostatic pressure, which is basically finding the total pressure on a metal plate if you stick it under the water. And evidently, people in engineering stick plates underwater, and so they want to know what the total pressure is. Hydrostatic just means water pressure, I believe. So far, so good. So I've got our first guy then. How do you find the center of mass in a 1-dimensional situation? So I want you to imagine this number line is a very thin piece of metal that doesn't weigh anything. But at these 3 locations, like there, and like there, you've put little weights, little things. At this point here, its mass is M1. At this point here, the mass is M2. And at this point here, it's M3. And X1, X2, and X3 are the X coordinates, right? So if you imagine that might be over at -2, that would be at 1, and this would be at 3, right? Something like that. Then, to calculate what's called the center of mass, what you're really trying to do is, can you imagine that pen represented the thing? You want to find a point where there would be a balance, so that if you stuck your finger on that pen, it would balance. Every object has a center of mass, right? And we're trying to find it. So you calculate m, little m, which is the total mass of adding them up. You calculate a thing called the moment, capital M, and you get that by essentially just multiplying the position with its mass. That's this thing. And the center of mass is this guy divided by that. Well, that's a very big picture kind of situation. So let me show you. Don't like that pen. Let me show you. Yeah, like that one there. An example of that. All right, let's suppose we had this fella here. And I'm going to put at this point here an object that has a mass of 20, maybe 20 kilograms. And at this point here, it's going to have 5. And at this point here, it's going to have 10. So somewhere between x is -2 and x is 3, there's a balance point. Can you imagine that where my pen is might be that balance point? So what would happen is if I put a little fulcrum, a little triangle, like a seesaw, it would balance, right? It wouldn't keel over to one side or the other. That's what the center of mass tells us. Right, so according to the process, we find the total mass, which in this case is 20 plus 5 plus 10. So that gives me a mass of 35. We find the moment, capital M, and that's 20 times its position at -2, plus 5 times its position at 1, plus 10 times its position at 3. And that's 35, take away 40, I make that -5. And so the center of mass, which is called x bar, is the moment divided by the mass, which would be -5 divided by 35, which simplifies down to -1/7. So -1/7 is about here. Have you noticed that it's slightly to the left of 0? So why is it to the left of 0, even although there's 2 masses on one side and only 1 on the other? Why wasn't it closer to the right-hand side, like maybe 0.2 or 0.3? What made this happen physically?
But -2 has more mass overall than the other two.
Yeah. Doesn't this have a bigger effect, even though there's only one of them, than these two? Does that make sense? Now, why would that be useful? Well, can you imagine that you had, I don't know, a girder. And on this girder, there were 3 posts of different masses. What we now know is where to put a single post so that that structure would be balanced. You see, if you were building something, wouldn't that be a balanced place to put the support girder? If you put the support girder there, wouldn't there be a tendency for this thing to lean over on whichever side of the major one? So people in construction, people who build things or design objects, are very often interested in the center of mass for all sorts of reasons. For instance, do you know if you want to find the center of a mass of a ship, right, which is a much more complicated version of this, but it's the same idea. Do you know the most stable ships have a center of mass which is near the center of the ship and as low down as possible? So you can imagine I was trying to draw a big container ship, right? You want the center of mass to be in the middle, and you want it to be really as low down as you can get it. That is the most stable position for the center of a mass. If the center of mass is too high, isn't there a tendency for that ship maybe to keel over to one side or the other in a strong wind, or when waves hit it in a particular way? If you've ever been on a submarine, which are basically that, right? Do you know that the center of mass of a submarine will be typically in the center of the submarine and very low down, or as low as they can make it? Now, if you change the center of mass by sucking in water or expelling water, and you move the center of mass forward or back, you will change the orientation of your submarine, and you will make it point up the way or point down the way, and guess if you did it enough, rise to the surface or sink to the bottom. So you can actually change the center of mass by changing the ballast, the location. And a lot of ships have things called ballast, which are basically, used to be in the old days, rocks that you put in your ship to try and change the center of mass to a more stable position. So they're a big history for you of why anybody would want to do that. Do we feel comfortable about how we calculated the center of mass in a 1D situation? Do you want me to do another one, or can I move on to 2D?
I have a quick question.
Yes.
So is the center of mass always at the center of, in this case, like a pole?
Well, it's not, actually, that's
mass.
not quite the center. Can you see that slightly to the left?
I'm sorry, I said the wrong thing. Is 0 always at the center of the pole?
Is this 0? I'm not sure your question.
I'm sorry, I had said center of mass when I meant 0. So if you have a pole, is 0 always directly in the halfway down the pole for our calculations?
Here? No, you can have, if what I'm getting you is correct, you could have a story where your masses like that. You see how 0 is quite skewed to the left here.
Okay. Interesting.
There was, yeah, there's no necessary reason for 0 to even be in the picture. I mean, couldn't I do one that went 1, 2, 3, 4, 5? You know, and in a way, isn't that just a scale, a label to put things on? You can shift the numbers around a little bit and it won't change.
Okay.
Okay, are we good with 1D? Can we move on to 2? Last chance to say no? Okay. This is how 2D works. So you imagine XY plane. We're like the origin because it's easier to see where things are if the origin's in the picture, right? And so in this case, I've got a mass over here, a second mass here, a third one here. This is the coordinates of the first, second, and third one. So the center of mass now is a point probably roughly where my finger is, right? Kind of here. And it's called X bar, Y bar. So how do you calculate it? Well, you calculate the total mass, which means you add up these 3, which is that. And then there's things called moments. Now, evidently from my other class, we get into a long conversation, which I'm definitely not going to do this time. They have done some stuff with moments, and it might have been in their physics class, I can't remember. Has anybody done stuff with the word moment being used? Okay, makes the conversation even quicker then. There's 2 guys that we use called the moments at Y and the moments at X. The moments of Y are mass times x1, mass times x2, mass times x3. And yes, that looks backwards. You notice how it's called my, even although it uses x's. And this is called mx, even although it uses y's. Why are they called that? Why isn't this called mx and my? I have no idea. I only do what I am told. Evidently, physics people do that. And if you do it that way, then we'll do it that way. So you get this moment by doing this calculation. You get this moment by doing this calculation. So where's the center of mass? X bar is this over this. Now, if you take this guy out of the way, doesn't X bar look much more sensible now? You notice how X bar uses the X coordinates, which is what you'd expect, right? And doesn't Y bar use all the Y's? So let's do an example. So -1, -2, 1, 2, 3. -1, -2, 1, 2. And let's have 3 again. Let's have a guy down here. That's at -2, -2, and his weight is 10 pounds. And then I'll have one over here, and its coordinates are going to be 2, -1, and he can weigh 5 pounds. And then we can have one up here, and it's going to be 15 pounds, and it's going to be at position 1, 2. So we are going to find the center of mass of this system. Me visually, I like to put in and pretend dotted lines. Can you see a kind of triangle which you typically should get? I'm looking for the center of mass of this. So can you imagine that this was a very thin piece of cardboard, and at the corners you put weights? And so the center of mass, as a very rough guide, is about there. You see where my finger is pointing, right? So I'm not making any attempt to say this is correct. I'm just saying that's where I think the answer is going to be. Now, you might think, nah, I think you're a bit lower or a bit more to the left or a bit more to the right, but that's my prediction. And according to my guy, it's going to be about 0.5, 0.1. And that is pure guessing, right? It's not that I've done this question before. Anybody want to add to that? Do you think it should be a little bit higher, a little bit lower, more to the left, more to the right? Has anybody got any gut feeling about changing my center of mass in any way? Because, by the way, this is a guess. It's not anything else. Guesstimate again. Megan, do you want to move this guy? Are you happy where I put him?
I think I like it. I mean, I guess you could probably put it a little closer to the 10 and the 15 and farther away from the 5, maybe?
So, somewhere going that way?
Just a little bit. I mean,
Right.
so
Or that way?
here's the thing I'm considering. The 10 is farther away from the 15 and the 5.
Right.
But the 15 and the 5 way more together. That'd be, I guess I'm not really thinking about it on the XY axis. I kind of am thinking it on a, like if I put a point midway between the 10 and the 15-5 line, that'd be between 10 and 20. So maybe like a third of the way over from 15 and 5. And then if I looked at the triangle the other way, between those two, I'd move it a little towards the 15, you know, so actually I'd say up and to the right a teeny bit if I really think about it.
Okay, so of the 3 that you're going up and to the right a little bit, okay? Let's find out. The total mass you get by adding all the weights together, and I guess it doesn't matter if my order's out because it's still the same total. They weigh 30 pounds. If you want to get X bar, you do M1X1 plus M2X2 plus M3X3. That basically is the guy that they call MY, right? That's the top bit. And you divide it by the total mass, right? So let's see what we get. This guy here is 10 and its x-coordinate is -2. This guy here is 5 and its x-coordinate is 2. And this guy here is 15 and its x-coordinate is 1. So you put this together and we get 0. No, we don't. We get 5. Divided by 30. So we get 1/6, which is 0.17. So it's actually this way. Find out what Y bar is then. Well, you go mass 1, which is 10, times its Y coordinate was -2, plus 5 times its Y coordinate, plus 15 times its Y coordinate. And that gets divided by 30 as well. And that's 30, and that's 25, and that's negative 5 over 30, which is negative 1/6. So x bar, y bar, the center of mass of this shape is basically 1/6, negative 1/6. It's kind of that guy there.
Oh, I had it the second time.
Right. But you can see how difficult it is to judge a center of mass from a picture, because the picture only tells you half the battle. Do you know if I change this 15 to 45,
I don't
I
think
changed
that
that.
that's a negative 5.
I think it's
I didn't
positive
count
5.
it.
It should
Is
be
it
a
up a bit?
positive 5.
Oh,
You have a negative 25 and a positive 30.
thank you. So actually, it's that fella there. So left and up, right? As I was saying, it's quite hard to judge on the picture, because doesn't it also depend on what the weights are, not just their location? Because if I made this 100, wouldn't I be pulling the center of the mass really close to this guy? If I made this weight 100, right? If I made this weight 1, wouldn't the center of the mass be pulled much more towards these two guys? If you built a triangle and you put weights on these three sides, then at this location here, at 1/6, if you put your finger on it, you would actually be balancing that very precarious triangle with weights on it, theoretically at least. And a joke just came into my head, so I've got to get out very quickly. What do you do if you get attacked by a group of circus performers? You don't know? You go for the juggler first. Oh, come on, I deserve at least one thumbs up. Come on. Okay, I got one. Sam is the only one who thinks that's funny. Oh, now I'm getting a sympathy thumbs up. That's just worse than having none at all. Okay, are we comfortable with center of mass in 2 dimensions, or do you want me to do another one of these guys? You know I can't count. The process is correct. You just be careful with the counting. Are we good? I'm going to move on if we are. If not, I'll do another one. Okay, I don't hear any dissent. So our next guy then. How do you find the center of mass then when your shape is this shaded bit? So it doesn't have points at each corner that weigh things. Can you imagine this piece of cardboard, same thickness, right? Same density. Where would the center of mass go? And I'm saying roughly where that asterisk is, right? But is there a way to actually find the center of mass when your shape is described as the area under a curve? And the answer is yes. And here are your 2 plug and chug formulas. The x coordinate of the center of mass is 1 over a, this integral. The y coordinate is 1 over a, this integral. And a is just the area under the curve. That's my dog Maggie decided she wants back in, so before she scratches her way through the door. Okay. So x bar, y bar, and a. So this is calc now, right? This is good old integration. So let's suppose I have the function f of x, and it's equal to the square root of x. And it's going to go from x equals 1 to x equals 4. And I'd like to find what the center of mass of that shape would be. So can you imagine y equals the square root of x, right? And can you imagine this guy is at 1. And this guy here. And we are trying to find the centre of mass of that shape. And I won't even guess. Okay, I'll sort of a guess. There, right? Kind of sort of it in the middle of the shape. Does that make sense? That's where it should go. So, first thing you do is you find A, which is the integral from 1 to 4 of the function dx. Well, we've done enough questions with square roots to realise that you use the power rule and you're going to have to convert it to x to the half. So that's add 1 to the power and divide by the new power. Evaluated at x equals 1 to x equals 4. And so that's going to get me 2/3 the square root of x cubed, evaluated at 1 and at 4. And that's going to get me 2/3 the square root of 4 cubed, take away 2/3 the square root of 1 cubed, 4 cubed, 2, 4, 8, 16/3, take away 2/3, I get 14/3. How does that look? Give you a few seconds to check my working and my numerical part in particular. Does that 14/3 look good? Right, we are moving on then. To get the x coordinate of the centre of gravity, it's 1 over a, the integral from a to b of x, f of x dx. And I'm writing down the other guy while I'm at it because okay. So x bar is going to be, well, 1 over 14/3. Doesn't that get you 3/14? So you're happy about 1 over a is just the reciprocal of this. The integral from 1 to 4 of x square root of x dx. Can someone tell me how to deal with that? How to deal with x square root of x? So
Combine the x's.
Combine the x's.
And if I do that as a fraction, are you happy about 3/2 in one go? So that means we can now do the power rule. Add 1 to the power, divide by the new power, evaluate it at 1 and at 4. Well, these two and this cancels, so what do I get? I get 3 on the top and I think 35 on the bottom. Are we okay with these two? Cancel 7, 5, 35, 3/5. Right. Now what do I get left? Well, I'm going to do, excuse me, that guy. That's 32 take away 1, which is 31. So that's 93 over 35. And 93 divided by 35 is about very roughly 2.7. Right, there's my guy. I'm a little bit out, right? I'm a little bit to the right of what it really is, but not bad. Oh, by the way, we only want the exact answers. The only reason I'm doing this is so I can figure out where it would be physically. Right, now, y bar coming up next. To get the y coordinate of the centre of mass, it's 1 over a, the integral from a to b of a half f of x squared dx. And 1 over a gets you 3/14. And the square root of x is the function. And this one comes out quite nicely. Oh, that 2 can come all over here and become 8. So the square root of x gets me x. And so 1/2.
A is 3/14, right?
Whoa. Thank you. Woke up. X equals 1 to 4. A half of 4 squared is 8. Take away a half. 15 halves. Is there anything here that cancels? 45 over 56, which is roughly about 0.8. So x bar y bar is 93/35, 45/56, or approximately 2.7 by 0.8. So 2.7 is probably more like here, and 0.8 is probably more like here. Not a bad guess. Would you agree? I'm just a little bit to the top right of it. Would you agree that green dot is also pretty much in the middle of the shape? Are we good with the process? I know it's a little bit on the long side because you essentially don't you have to do 3 different integrals. But are we comfortable with the process? Because it is, to me, anyway, it's a plug and chug, right? There's 3 things you need to get, and each one of them, right, you know what it is. It's an area of some kind under a curve. Okay. For the last few moments then. Oh, while I'm getting ready for the last question, say hi, get attendance. Okay, here goes. The last kind of version of this type of question is we want to find the center of mass of a shape that is made out of the intersection of 2 curves, right? In this case, square root of x, x squared. And in this case, we start at 0 and we finish at 1. Which means we're going to have to adapt the plug and chug formula to account for these 2. Now I'm going to call this guy here f of x, and I'm going to call this second one up here g of x. And if I do that little vertical rectangle that we very often use so we can figure out who's high and who's low, how are we going to get the area of that shape? Well, it's going to be the integral from start to finish. I know this case it's 0 to 1, but in general, start to finish. And won't you do f of x, take away a g of x dx? Would you agree that's how you adapt the area issue? Single curve, area between 2 curves. So far, so good. Now, the x bar formula is 1 over a, the integral from a to b, x times something. It used to be x times one function called f of x. What is it going to be now?
f of x minus g of x.
Correct. And then y bar is 1 over a, the integral from a to b, of 1/2 There is a issue here, and I want to be very careful when I do this, because this is the one where people screw up on. There are two alternate versions of what this might look like. Only one is actually correct. And the two alternate versions, couldn't it be f of x take away g of x, everybody squared? Or you square them first and then you subtract them. One of those two is actually the right answer, and the other one doesn't work. But unfortunately, it's not that uncommon that people pick the wrong one. And I kind of know why. They want to pick this one because everybody else seems to be this one, when in fact it's that one. So it's 1/2 of f of x squared take away g of x squared. Now I'm going to try and convince you why this one actually makes sense. If you take this equation here, can't you split it up? Like that. Can you see I would say x times this guy, x times this guy, right? Now if you take this one, which is the correct answer, you can also split it up. And can't you take the area? Do you see that when you look at it this way, don't they now kind of make sense of why you got what you got? Now you might think that it doesn't matter. You might think, well, if I did it the other way, right? If I did it, subtract them and square, I'll get the same answer. No, you won't. 7 take away 3 squared is not the same thing as that. 7 take away 3 is 4, and 4 squared is 16. This guy, it's a square, is 49 take away 9. Do you see they're not even close? Okay, so if I convinced you that this is the correct adaptation when it's the area between two curves. So I got our little guy here set up. So the area is going to be the integral from 0 to 1 of square root of x take away x squared. It's basically f of x take away g of x dx. And you'll get that guy, whatever it is. X bar will be 1 over a, the integral from 0 to 1 of x times that guy. And then you'll get what you get. And y bar will be 1 over a, the integral from 0 to 1 of 1/2 this guy squared, take away that guy squared. Now, I haven't got enough time to fill in the details, but you got the gist of how that would work. That would be x take away x to the 4. That would be x to the 3/2 take away x cubed. And that would be x to the half, take away x squared, and everybody would be a power rule with some really, really ugly looking fractions. And if I was a gambling person, and I imagined an invisible dotted line going through this shape, I wouldn't be at all surprised if the center of mass would be there. Would that make sense? Just by the symmetry of the shape. Agreed? Right. I've got 3 minutes, so why don't I use it? Here goes. Suppose it's a circle. Where's the center of mass?
The
Center of the
center of the
circle?
circle.
Yeah. Suppose it's a circle. This circle, a specific one. And it's only the top half. I don't need any calculus to figure out where the center of mass of that shape is. Well, let me redo that. Where is the x coordinate? I should be more specific. Where is the x coordinate of the center of mass?
0 still?
0. Now, the y coordinate, I don't know. I'd have to calculate it. But what that tells me is, if you draw a quick sketch of the circle, couldn't you maybe save a little bit of work by knowing the x bar is 0 without having to do any calculations, and only work on the piece that you know? So if your shape has symmetry, any kind of symmetry, right? So if it's an isosceles triangle, won't x bar be right down the middle? If it was a rectangle, wouldn't it be down the middle and across the center? It would be there, wouldn't it? So if there's any kind of symmetry, the center of mass will be on the axis of symmetry, right? So a vertical or a horizontal axis of symmetry. X bar will be on the vertical, and if it's got horizontal symmetry, and Y bar will be on the horizontal symmetry. So you can sometimes reduce your workload by only calculating one. I think we learned some cool stuff today, and I told a really funny joke to which only 3 of you laughed. So I am quite disappointed in everyone. You'll have to do better next time, or not. I did send out an email with your grades. No, I didn't say I got it. Some of you are nodding, right? If for some reason, and I've given up trying to fix the spreadsheet, I'm sending it out, it just ain't arriving. For maybe it's in your side, maybe it's going straight into spam. If you haven't got your grade, shoot me an email and I will just send it to you as a one-off, right? So if you've got yours, you don't need to, of course. But if you're not, if you haven't received it, shoot me an email and I will give it to you. Or do what one of my students in the other class did. He said, oh, it's in my student email. I didn't know that. It's only one of 2 places, student email or the email address that you used in WebAssign when you signed up. That's the only 2 that I use. So that's where you go to look. And I'm out of here. I'll hang, well, wait a minute, I should hang about. Anybody get any questions? I'll hang about. Apart from that, see you tomorrow, where we get to do some more centers of gravity and hydrostatic pressure.
Have a good day.
You too. We learned some cool things today. And
Yeah.
you liked my joke. I saw you laughing.
Yeah, I'm gonna share it as soon as I get off of the meeting with my brothers.
Oh, you think they'll appreciate that sense of humor?
Oh yeah, definitely.
Okay.
Okay, have a good day.
You too. I'm still here, so is any of you 3 got a question that you need to ask me?
I'm just double checking. It doesn't look like I got the grade, so I'll send you an email.
You're right. Just send me an email and I'll shoot it back to you. I can't explain why some people don't get it. It's whatever. It's gremlins, right?
I don't know. It's really weird. There's been a lot of stuff going on. Like last year, I lost all of my Canvas because I have a student account and I work for the vet center. So I've got a staff account. So when they did the whole conversion for CTC Link, I lost everything. And there's just been weird stuff going on like that ever since. So it might be part of that.
I don't know what it is. I think my gut feeling is always to blame CTC just because I can. I don't know if it's anything to do with that. It could just be weird stuff.
No worries. I'll send you the email here in a minute or two.
Right. I'll try and get back to you as soon as I can. I think I've got I know I've got something to do, but I can't remember what it is. So you might want to give me an hour. Right. I'll get it back to you as soon as I can.
No worries. I appreciate it. Thanks.
Not a problem. Sean Mungoon, have you got anything?
Yeah, I actually have a question about next Wednesday, the 25th.
Yes, you're not going to be here.
Yeah, I have a meeting at, wait, do you already like know that I had a meeting, or is there just like not going to be class? Or
There's just not going to be a class
okay.
because Wednesday's going to be a non-student day. I'm going to be at conference and whatever, but not
Okay.
any of the students.
Oh,
So
so Wednesday is just not a non-student day, pretty much.
Yeah, so you won't have a class.
Oh,
And
okay.
there won't be a-
Fantastic. Yeah, I was
Right,
gonna
so
call
that
out.
cures your problem, whatever the problem was going to be.
All right, well, that's all I had. So have a good day.
You too. Monkoon, have you got a question? Last chance, I'm going to leave then.